Hey everybody, welcome to Algo Expert. In this video, we're going to be covering Big O notation. More specifically, we're going to be looking at how exactly we measure complexity, and we're going to be looking at the notation that we use to describe complexity in algorithms. On top of that, we're going to be going through a few practical techniques that you can use in your coding interviews to determine the complexity of your algorithms. So if we remember from the complexity analysis video, we said that time complexity measures how fast an algorithm runs, and space complexity measures how much memory it takes up, how much auxiliary memory it takes up. But what does that really mean? Take time complexity, for example. Let's say that we have an algorithm. How would we express that algorithm's time complexity? Would we say that the algorithm has a time complexity of 5 seconds, of 10 milliseconds? No, it turns out that we wouldn't say that. In fact, that wouldn't really have much meaning. It wouldn't be very valuable. And so now let's look at an example to understand why that wouldn't make sense. So in front of me here, I've written in pseudocode 3 different algorithms: F1, F2, and F3. All 3 of these algorithms take in an array as an input, which I've called A for the purpose of this example. A is indeed an array of length n, and we're going to assume that it's an array of integers for the sake of this example. And so the first algorithm, F1, just returns the sum of the integer 1 and of the first integer in the array. And for now, we're just going to assume that this is always a non-empty array. The second algorithm, F of 2, just sums up every element in the array. So you can imagine that it iterates through every element in the array and sums them up. And finally, F of 3 generates a bunch of pairs of numbers in the array. And more specifically, what it's going to do is, let's imagine our array were 1, 2, 3. It's going to iterate through every number in the array. And at every number, so let's say we're at the number 2 at one point, it's going to reiterate through every number and generate the pairs. So for instance, for this array, we would basically get 1, 1, 1, 2, 1, 3. Then we would get 2, 1, 2, 2, 2, 3. And then we would get the same thing with the number 3 as the first number. So you can imagine that you could write this algorithm F3 by just writing 2 nested for loops. Okay, so these are the 3 algorithms, and now let's assume that we wanted to express their time complexity, and assume that we were going to use what we said before, the suggestion that we gave of expressing the time complexity in seconds. Basically, how many seconds or milliseconds does it take to run these 3 algorithms? And here, by the way, if you're interested, you could actually pop open your terminal, write these 3 algorithms in the language of your choice, maybe Python for simplicity, and you could either run them with various inputs to see how fast they take, just, at a glance, or you could even do something a little fancier and import an actual library that tracks how much time elapses between lines of code, and you could actually track how long it takes to execute these 3 algorithms. But so I jumped the gun a little bit here. We have these 3 algorithms, and now let's assume that we run all 3 of these algorithms with our array A, when the length of the array n is equal to, let's start with 1. So literally, we just have 1 number in the array. If you were to run all 3 of these algorithms with an array of length 1, they would all run basically instantly. Now, if you are actually tracking the execution time of the algorithms, you might get slightly different values every time, even for the same algorithm. For instance, if you were to run F1 multiple times with an array of length 1 and you were to track the time that it takes to execute, you might see slightly different values. You might see 1 millisecond, 5 milliseconds, 2 milliseconds, depending on when you run it. The reason that you might see varying values is because there's a lot of stuff going on in your computer at once, and there's a lot of stuff that can affect the execution time of an algorithm. But the point is, these algorithms would run very fast, and they would all be in the same ballpark. Okay, so maybe we could describe these algorithms as 3 algorithms that run in 5 milliseconds time complexity. But then what if we were to increase the size of the array from n equal 1 to n equal 1,000. If you were to rerun these three algorithms with an array of size 1,000, you would maybe start to see something a little bit different. The first algorithm wouldn't change. It would run just as instantly, just as fast, with maybe slightly varying execution times in the order of milliseconds every time. The second algorithm would also run pretty much instantly, but the third algorithm would start to take a little bit of time to run. It would probably take a few seconds to run. And then, if you were to increase the size of this array once more, this time from n equals 1,000 to n equals, let's say, 10 million, so you would add 1 0 here and then another 3 zeros, 10 million, and then you were to run these three algorithms once again, the first one wouldn't change. It would still be almost instant in the order of milliseconds. The second one would start to take a little bit longer. It would probably take a couple of seconds to run. And then the third one would likely run forever. And I wouldn't encourage you to try this out with a third one because it would probably just hang and your computer might crash or you might have to close your terminal. Okay, so why did I go through all these examples? Well, first of all, it was to show you that it's basically impossible to describe the time complexity of these algorithms in seconds or in milliseconds because it really just doesn't make sense. Clearly, we saw that depending on the size of this input array, these algorithms might all three run exactly with the same speed almost instantly when we had the array of length 1. But if you increase the size of the input by a lot, then these algorithms start to really run with different speeds. So does that mean that you would describe the time complexity of these algorithms as something along the lines of, oh, if you have a small input array, then this algorithm runs in, less than 10 milliseconds. But if you have a bigger input array, but that's less than 10 million, then it runs in under a second. But then if you go past 10 million, it's over a second. No, that just doesn't really make sense. It's not meaningful. The one thing, however, that we did notice by going through this example of running these three algorithms with these various inputs is that clearly the speed of these three algorithms is very dependent on the size of the array, or at least the speed of two of these algorithms. The first one actually wasn't dependent on the size of the array, but these two, clearly their speed was dependent on the size of the array. And so this is where we can start to see something a little bit more meaningful. It's more meaningful to describe the time complexity or the speed of these algorithms by saying that it's affected by the size of the input, and as the size of the input grows, it's affected more and more. Like clearly, for instance, F3 was affected a ton by the size of the input, whereas F2 wasn't affected that much, but it was affected a little bit, and F1 not at all. That's much more meaningful than to try to give this weird arbitrary, seconds or milliseconds, or to try to frame it in between some arbitrary range of input sizes. So this now brings me, of course, to the real definition of time complexity, and in turn, the real definition of space complexity. I think that for the rest of the video, or for most of the video, I'm primarily going to look at time complexity, but you can apply all of the concepts that we're going to be covering in this video to space complexity as well. Space complexity is essentially equivalent to time complexity in how we measure it, at least with big O notation, which we're going to get into in a second. But so the real or more accurate definition of time complexity is not just the measure of an algorithm's speed, but it's more specifically the measure of an algorithm's speed or runtime as the size of the input to the algorithm increases. We care about measuring how fast an algorithm runs as the size of the input increases. We saw that for the first algorithm, the speed of this first algorithm was not affected by the size of the input. As the size of the input increased, the speed of F1 wasn't affected. The speed of F2 was affected, not that much, but it was visibly affected, and the speed of F3 was completely affected. It was very visibly affected. So now, as far as time complexity, how we actually express this time complexity, because again, here I keep using just English to say that, oh yeah, it wasn't affected, it was affected a little bit. So this is where we actually have to have some notation for it, and this notation is called big O notation. For the first algorithm, F1, we would say that it has a time complexity of O of 1. O of 1 time complexity, which can also be read as constant time complexity, basically means that as the size of the input increases, and here the variable that we're really caring about is this variable n. N is the name of the variable that we've given to the length or size of the input array. But so as n increases, the speed of f1 remains constant, hence constant time, O of 1 time. For f2, the time complexity is going to be what we call and write O of n time complexity. This can also be read as linear time complexity. This means that as the size n of the input array increases, the speed of the algorithm increases linearly. And here, the way that you can think about it conceptually is, if we're summing every value in this array, we're going to have to traverse through every value, right? We're going to have to traverse through n values. Therefore, as n increases, we're going to have to go through however many more data values are in the array. So we're going to do as many iterations through the array A in the sum function as there are elements in this array, and the number of elements is n. Therefore, we would express the time complexity of this algorithm F2 as O of n, linear time complexity. Finally, for F3, the pairing function, remember that we had this array where we said we traverse through every number in the array, and at each number, we retraverse through every number. So let's say we have an array of length n. At the first number, we do n iterations, right? We traverse through the entire array, so n iterations. Then at the second number, another n iterations. At the third number, another n iterations. We do that n times, so we're going to have a time complexity of O of n squared, n multiplied by n. So here there are a few very important things that we have to talk about. So let's take a step back and really study this big O notation. Because right now I still wrote these values down sort of magically, so I want to make sure that we really understand where these values come from, what these expressions mean, and so on and so forth. So in English terms, we said that with time complexity, we're measuring the change in speed of an algorithm with respect to the size of the input, right? That's very important. And there's actually a mathematical term for that. There's a mathematical term for analyzing the behavior of a function as the input of the function increases and tends toward a value, like for instance, infinity. And it's called asymptotic analysis. It's a very fancy word, but all it means is we're going to study the behavior of a function f of n, as the value n tends towards infinity. And here it's exactly what we're doing with big O notation, and in turn, complexity analysis. Basically, when we're dealing with time complexity or space complexity, we're expressing these concepts asymptotically using big O notation. And so big O notation, the way that you should read it, if you read, for instance, O of n, you should say, okay, this means this is an asymptotic analysis of the behavior of my algorithm. And if we're talking about time complexity, it's going to be specifically the speed of the algorithm. If we're talking about space complexity, it's going to be specifically the amount of auxiliary memory that our algorithm takes. But so the way that you would read O of n is you would say, okay, the speed of my algorithm increases linearly as n, which is the size of my input, increases. For O of 1, you would read it as the size of my input n increases and tends toward infinity or some huge value, the speed of my algorithm, or the amount of auxiliary memory or space that my algorithm takes up, remains constant. Now here, one thing that you might still be wondering is what unit are we really dealing with here? Because for instance, this O of 1 expression here, you might still be asking yourself, 1 what? What is this 1 referring to? Is it seconds or milliseconds, or is it some weird abstract thing? And it turns out that it's more the latter. It's more this weird abstract thing, but more specifically, the unit that we use for time complexity is what we're going to call an elementary operation. And so it turns out that 1 plus a of 0, or accessing a value in an array at a given index 0 here, this constitutes an elementary operation. But perhaps a better way to really grasp this is to go back to our memory video where we explained how data is stored under the hood in memory. And recall that we said that data was stored in these memory slots in our memory canvas as bytes. And so, for instance, when we were dealing with integers, we said that integers were typically fixed width integers, meaning that they took up a fixed number of bytes in memory. We gave the example of 32-bit integers or 64-bit integers, where they took 4 bytes or 8 bytes in memory. But so you can think of a truly elementary operation as accessing a single memory slot. If you're accessing or reading a single memory slot in memory, you can imagine that that's really one of the most elementary operations that your computer can perform. So accessing a value in a single memory slot would take constant time. Okay, but so then you might be wondering, in this first algorithm, F1, we're adding 2 numbers, so we have to read 2 numbers in memory. And like we said, integers are typically going to be 32-bit integers or 64-bit integers. And if they are 32 or 64-bit integers, 4 or 8 bytes, respectively. We just said that. So here, let's say we were dealing with 32-bit integers, we would actually probably be doing 4 elementary operations just to read the number 1, and then 4 other elementary operations, perhaps even more, to read this number. I say perhaps even more because we also have to actually access the number, find where this number is given this index, but that's going to be part of the arrays video. But so this would actually be more like 8 elementary operations if we're dealing with 2 32-bit integers that are each 4 bytes. So in theory, this O of 1 here should actually be written as O of 8, because we're doing 8 elementary operations. And I'll add a question mark here because I'm saying that this might be something you're asking yourself. And this is where it's very important, it's exceedingly important to really understand how asymptotic analysis works. When we're doing asymptotic analysis, meaning analyzing the behavior of a function, or in our case, an algorithm, given an input n, when n tends toward infinity, we don't really care about the exact number of elementary operations that we're going to be performing, so long as that number doesn't have a relation to our input n, or the size of our input in the case of an algorithm. So here, O of 8 doesn't have any relation to the size of our array n. As n increases, we're still doing 8 operations every time, because we're still going to be reading through 4 bytes of memory with 1, and the same thing with this number. So this 8 remains a constant factor, and so from an asymptotic analysis point of view, we just don't write this 8, we basically simplify it to constant time, which again is denoted as O of 1. So here now I'm starting to get into some of these little techniques that you're definitely going to want to use in your coding interviews when you're expressing your algorithm's complexity. If you ever find yourself writing an algorithm that has a bunch of elementary operations in it, and here we're not even talking about just, how many memory slots a certain integer is going to take in memory, we're also talking about bigger elementary operations, like here, additions or multiplications, declaring variables. all of these things that under the hood are doing a fixed amount of, let's say, memory slot reads, all of these things are going to be constant time. And if you have multiple of them, you're still going to bring them down to constant time. And so we'll look at a few examples in a few minutes. But the second thing that relates to what we just said that's very important about asymptotic analysis is that we really only care about the very significant factors in our complexity. So what I mean by that is, imagine we had an algorithm, let's call it f of 4 of a, that was equal to some combination of these three algorithms. So you can imagine that these three algorithms would be run in f of 4. F of 4 would suddenly have a time complexity of, I'll put it down here, it would have O of n squared plus O of n plus O of 1. And you could write this as, let me erase this to give myself some space, you could write this as O of n squared plus n plus 1. But here, what I was hinting at just before is that as n tends toward infinity, this n squared becomes gigantic when compared to this n or to this 1. Or a different way of putting it is that this n and this 1 become insignificant next to this n squared. And so from an asymptotic analysis point of view, this expression that we just wrote down here would actually be simplified to O of n squared. And we would just put O of n squared. We would not put O of n squared plus n plus 1. Similarly, imagine if in this algorithm F4, we actually ran F3 twice. So we had 2 times the algorithm F3. We would actually have suddenly a complexity analysis of O of 2n squared plus n plus 1. But again, here, this 2 is a constant factor. This 2 doesn't change when n changes. So from an asymptotic analysis point of view, we say that because this factor is constant, it doesn't matter to us, so we're going to just remove it. So let's quickly summarize everything that we've covered so far. Then we will look at some of the other very common complexity values that you'll see, because so far we've looked at constant time, linear time, and n squared time, but we haven't looked at other ones. There are a lot of other very common complexity values. And then after that, we'll go through a few examples. But so to summarize, so far we've said that time complexity and space complexity actually measure how the speed of an algorithm or the extra memory an algorithm takes up, how these two things change as the size of the input of the algorithm increases. These complexities are expressed asymptotically using big O notation. When we're dealing with big O notation, the unit, at least for time complexity, is going to be the number of elementary operations that we're performing. With space complexity, it might be something along the lines of the number of memory slots that we're using up. But the key thing with asymptotic analysis is that when we're dealing with constant factors, we always bring them down to 1. We don't care about a constant factor that's greater than 1 because the point is it remains constant as the size of the input increases. So there's no such thing as O of 8 or O of 16 or O of 20. It's always O of 1. This explains conceptually why the fact that we have integers that might be stored using 8 bytes in memory or 4 bytes doesn't really matter. Dealing with a single integer still remains an O of 1 operation, or a single integer still takes up only O of 1 space. And we said that when we have more complex big O expressions, like O of n squared plus n, we always drop the smaller terms because these smaller terms become insignificant as n tends toward infinity. So now let's look at some of the very common complexity values. So I'm going to actually clear the entire screen here. And we said that we have O of 1, that's the basic one, constant time. And here I guess I'll just speak about time complexity again, but this applies to space complexity as well. Then we said that we have linear time. Now, it actually turns out that there's something in between constant time and linear time, so I'm actually going to move this O of n down here. There's something called logarithmic time, so I'm going to write it O of log of n, and we're going to be covering the concept of the logarithm, or of log of n, in the next video, so be sure to check it out to really understand what log of n is. It's probably the most mathematical aspect of coding interviews, mainly because complexity analysis itself is also pretty mathematical, but log of n is something that tends to scare candidates, so don't worry, we'll be covering that in the next video. Then there's O of n squared time, and here we also have other things like O of n cubed, O of n to the fourth, and so on and so forth. And here, this is actually one of the only times in asymptotic analysis where a constant as an exponent, we don't actually drop it down, because an exponent really does blow up the value n here. So for instance, O of n to the fourth is not at all equivalent to O of n to the second. Like O of n to the fourth makes O of n squared become tiny. So if you do have an expression like O of n to the fourth plus n squared, you would actually drop the n squared, and n to the fourth is the only thing that you would care about. Now here, just like above with O of log of n, I actually lied. There's something in between O of n and O of n squared, and it's O of, I'll move this down here, it's O of n log n, so n multiplied by log n. As you can imagine, if log of n is smaller than n, then n multiplied by log of n is going to be smaller than n multiplied by n, which is n squared, so that's why this fits in between here. And then we actually have even worse complexities here. We have things like O of 2 to the power of n. This one is a really bad one. And then even worse than that is O of n factorial. O of n factorial is one of the worst ones. You can imagine the reason n factorial is worse than 2 to the power of n is because here you do, 2 times 2 times 2 n times, whereas here you do n times n minus 1 times n minus 2 all the way to 1, where most of the values here are greater than 2, and you do this n times. So n factorial is definitely going to be worse than 2 to the power of n. And then even beyond this, there are worse complexities where you can put some of these together. For instance, you can imagine n factorial multiplied by 2 to the power of n would be really bad, but we're not really going to write them down. These are the most common ones that you need to know. And here I would highly encourage that you look up a complexity analysis graph. You can do so very easily. Just Google complexity analysis graph or big O notation graph, and you'll be able to really visualize what these functions look like, and you'll understand really how much better something like log of n is compared to n, or how much something like n log n is compared to n squared. Here I can very quickly jot it down. You can imagine that O of 1 looks something like a straight line here. It's just literally constant at the bottom, so definitely there isn't a curve here. It's just straight. Then log of n is something like this. It plateaus very quickly. Then n linear is something like this. N log n is something like this. N squared is something that curves up. 2 to the power of n curves up even faster, and then n factorial even faster. And so looking at a chart like this can be a nice way to visualize these various complexities and to really understand why something like log of n, which was this one that plateaued very quickly here, is so much better than basically all of the other complexities except for constant time. Like, the bigger your input n gets, the more something like n squared becomes really bad. If you're operating at Google scale, for instance, where you're dealing with billions, if not trillions of data values, then having an algorithm that runs in n squared might be really bad. Maybe it's the best you can do, in which case that's fine, but it's still important to know how something like n squared relates to something like log of n. So now we're going to look at a few examples before we finalize the video, but first I do want to mention one more thing, which is that big O notation, what it refers to, at least in the context of coding interviews, is the time complexity or the space complexity of your algorithm in the worst case scenario. Now, the reason this is important is because there are certain algorithms. Good examples of such algorithms are sorting algorithms like quicksort and merge sort, which we cover on Algo Expert. Some algorithms like those have different complexity analyses depending on basically the scenario. So for instance, when you're dealing with a sorting algorithm like quicksort, it has a best case scenario, it has an average case scenario, it has a worst case scenario. Depending on the way the input is structured, quicksort might have a worse time complexity, for instance. But so in the context of coding interviews, when we use big O notation, we typically always refer to the worst case. It's almost always understood that we're referring to the worst case. Because we don't really care about the best case scenario. We don't care about what happens when things go great. We care about what happens when things go bad. Now, to be honest, in coding interviews, most algorithms aren't actually going to have different complexities in the worst case or in the average case or in the best case. If they do, like for instance, something like quicksort, then it's typically better to clarify with your interviewer that you're dealing with the average case time complexity or the worst case time complexity. But for most algorithms, there isn't even going to be a difference. And it's just important for you to know that when you're saying big O, you're implicitly implying that you're talking about the worst case scenario. And here, one little note that's important to say for those of you who have a very academic background, who may have taken advanced algorithm classes in computer science or math, you may have heard of big omega or big theta. They're concepts related to big O. Forget everything that you know about these concepts and about the academic version of big O that you know, and trust that in the context of coding interviews, big O is the only thing that you care about, and big O refers to the worst case complexity. It's very important. This is what the industry has decided on. This is what the industry has sort of accepted. We deal with big O notation in coding interviews. Okay, so that was my final little point. I'm going to erase the screen one more time, and we're just going to go through a few quick examples where we're going to apply a few of these techniques that I said before of dropping the constants to show you how you could actually compute or figure out the complexity of your algorithm in an interview. So let's assume that you've got an algorithm that does a bunch of elementary operations. It sums up a few numbers. It declares a few variables. You declare an array of length, let's say 3 all the time. This is going to be an algorithm that might run in O of, 25, but that would be brought down to O of 1. So you would actually never want to say O of 25. O of 25 just doesn't really make sense. You'll notice that on Algo Expert in the questions, I often do stuff like this where I say O of 25, or rather like O of 2, O of 3, and then I cross it out and say O of 1. That's because I want to very explicitly tell you how I got to O of 1, but really it doesn't make that much sense, where the point is we're talking about constant time. Now let's say that you had an algorithm that traversed through an array, and at every element just did nothing. It just traversed through the entire array. That would be an O of n algorithm. Now let's say that you traverse through the array once from left to right, and then once from right to left. That would be an O of 2n algorithm, but again, you would drop the 2 because that's a constant, so it would just be O of n. Now imagine that you had this algorithm that we just did, where you go from left to right, from right to left, and then we also had the pairing algorithm with 2 nested for loops that ran in n squared. Like we said before, that would be O of n squared plus 2n, so we would drop the 2 here because we just dropped it above, and this n here would become meaningless next to the n squared. If we had an algorithm that was something like O of n cubed plus log of n plus 3, once again, you would drop the log of n and the 3 because n cubed is the biggest, most powerful element. Now here's an interesting example that we can end this video on. Assume that you had a function or an algorithm that took in 2 input arrays. The first input array had length n, and the second input array had length m, and you summed both of these arrays together. Then you would have something like O of n plus m time complexity. And you can imagine that if you created a new array of length n plus m, then you would also have O of n plus m space complexity, because you would be taking up extra space apart from the 2 input arrays. But now what if you had this algorithm above that we used here, where we had the pairing and the thing from left to right and from right to left, but we did the pairing with the second array, the array of length m. So you suddenly had something like O of m squared plus n, or plus 2n. We know that we dropped the 2. Do we also drop the n because m squared is bigger? Because we said that n squared is the bigger term. Here, this is a really important point, so perhaps it was a mistake to put it this late in the video, but no, you would not drop the n here because n is not the same variable as m. With asymptotic analysis, like we said, you care about the behavior of a function as the input increases and tends toward a value. Here we have two inputs, so we want to know the behavior as it relates to these two different inputs. And you can imagine that there's actually a scenario where m squared is tiny compared to n. Imagine m is equal to 2 and n is equal to a billion, or even just like 10, then m squared would be smaller than n. So that's why when you have two variables, you do always want to keep both variables. So if you had something like, let's say, O of n factorial plus log of m plus 2n plus 3. I know this is a very complicated big O expression, but here you would drop the 2n. First of all, I guess you would drop the 2. Then you would drop the 2n because 2n is nothing compared to n factorial. Then you would drop the 3 because 3 is nothing compared to log of m and n factorial, but you would not drop the log of m because the log of m depends on m, which is not the same as n. And so that's it. That's big O notation. It's an incredibly important concept. It's very important that you master being able to derive the complexity of your algorithms in a coding interview. And the good news is that in the remaining data structures videos on Algo Expert, we cover all of the space-time complexity implications of the various popular data structures, and in every single Algo Expert question video, we also cover the space-time complexity analysis of the solutions. So with that, I really hope that you found this video informative, and I'll see you in the next one.